My name is Megan Spengler, and this is a presentation for my Data Mining 2 course at UCF, where I will be building a classification model and walking you through the steps. Here's the agenda for my presentation. First, I will give a quick overview of the data set and the project goal. Next, I will discuss my methods for data prep and exploration, followed by model building and model evaluation. And I will conclude my presentation with the model results and any actionable insights from the model I created. First, we have the data overview. So I'm using this data set to perform classification of water quality in urban environments. The target variable is a binary classification variable called isSafe. So whether the water is safe or not, and equals 0 when it is not safe, 1 when it is safe. The data set has 20 predictor variables, which include different chemicals, viruses, bacteria, all found in water. In urban environments, they are continuous predictor variables, and the data description also was provided and gives thresholds for what level of the predictor is considered dangerous. So for example, any value of bacteria over 0 is considered dangerous. And this data source was found on Kaggle. So for data preparation, my first step was when I load in the data, I'm going to create a train test split that I can use later when I am testing my model and evaluating the accuracy. So next, I just used the basic summary function in R to get a quick overview of the data, which showed me there were 3 out of the 9,000 or so observations that had a missing target variable. So I just went ahead and removed those observations since there were not a significant amount of the data. And next, I use the threshold values provided to convert the continuous predictors to binary, where they equal 0 if the variable is over the threshold and considered dangerous, and equal 1 if the value is below the threshold. I also used this to evaluate the number of factors. So if a variable, after converting to binary, if it only had 1 factor, I just went ahead and removed it from the data set because it wouldn't be telling me anything. And the biggest issue I found when performing this data exploration was that the target variable was very imbalanced. And one other thing to note, my reason for converting the predictor variables to binary is because they were typically easier to work with in the models that I plan on creating, which are logistic and decision trees. So on the left, you can see a visualization of the target variable is safe, and the number of unsafe observations is way higher at 89%. You can see the safe observations there's only 11%. So this presents a big problem when you're creating models because you'll get a bias towards the majority classification. So the model will most likely categorize the majority of the observations as not safe, even if that's not true. So to fix this, I used upsampling technique from the carrot package on the training data, not the test data. So you can see the second bar plot has an equal number of observations for both safe and not safe data, not safe water quality. Next step was to explore all of the 20 predictor variables, or I believe there were 18 after I removed the ones that did not have 2 factors. So for each predictor variable, I created a bubble plot that compares the predictor variable to the target class. They are sized by number of observations and colored by bin percent. So we're looking for large bubbles that are red or blue. So this example, silver, is clearly not a good example because the 4 bubbles are pretty much equal in size. So they don't really tell you anything about the relationship between the amount of silver in water and whether it's safe or unsafe. Honestly, none of the predictor variables were ideal, but this variable chromium was one of the stronger ones when looking at the bubble plots. So you can see that when chromium equals 1, meaning it's at a safe level, 71% of the observations lead to safe and, 71 are unsafe and 29 are safe. So there's a pretty big distinction there. And the distribution between the levels of chromium in terms of frequency or number of observations, it's not equal, but it's closer than a lot of the others. Cadmium was another good example, relatively good, where at least we have bubbles falling in the low and high bins in terms of color and percentage, and the number distribution between the 2 class levels is, it's not even, but it's not too extreme. So next, I created a correlation plot to uncover any predictors that are strongly correlated. So we can see that nitrates and silver are relatively strongly correlated with chromium. The 2 red arrows pointing to those. So the larger the bubble and the darker the bubble means the higher the correlation, which we do not want. So chromium was the strongest predictor I found from the bubble plots I just showed previously, and neither nitrates nor silver had good plots, so I went ahead and removed those from the data set and kept chromium for model building. So this concludes the data prep and data exploration, and now we are ready to move to model building. So now that that is complete, I will start with logistic regression, which it's always a good choice for classification models. It's relatively straightforward to explain to stakeholders. Most people have heard of logistic regression at least, and it handles binary predictor variables as well. So in building this model, I started with all of the remaining 16 predictor variables and interactions between all of the variables. I ran the model and then removed any predictors that had an insignificant coefficient. I repeated this multiple times until I was left with only significant predictor variables. So here are the results of the final logistic regression model. The accuracy for the training set was 72.23, and the testing accuracy was 72. They're pretty close, but testing was slightly lower, which is a good sign because it means if it were higher, then we would be overfitting. And we can see a bar plot of the actual classification values colored by the predicted values. So you can see that for the test data, 76% of the unsafe observations, or class equals 0, were correctly classified. That's the pink. And then we can see 70% of the safe observations were correctly classified, the blue. So class equals 1. So this is pretty good. And the second model type I chose to make was a decision tree. These are a favorite among data scientists because they provide a great visual representation of the decision-making process. They're easy to interpret. They really just they tell you yes, no, the percentage of being right or wrong. And it's also easy to see which predictors are the strongest. So you can see kind of which ones are the most important, which ones to pay attention to. So when I started building this model, I didn't add any constraints. I didn't include any depth limits. And then here was my final decision tree. After pruning the decision tree, I set a max depth of 3. This is the final result. And no surprise, chromium is the top predictor at the top. So if you were to guess the water quality based on the level of chromium alone, you have a 50-50 chance of being correct, which is not horrible. And then next is chloramine and cadmium, followed by aluminium on the left, which were all stronger predictors that I identified in the data exploration step. So this kind of validates my findings from the data exploration. The accuracy for this decision tree model is similar to the accuracy for the logistic regression model. It's slightly higher. The training accuracy was 76 and testing was 73, which was 72 for the logistic regression, so this barely beats it out. And then we have a bubble plot of the confusion matrix for the testing and training data. And the percentages on these bubbles represent the percentage of observations, of total observations. So if we're looking at the test data set, we have 37% of classified class equals 1 and predicted, class equals 0 and predicted equals 0. And then 35% is class equals 1 and predicted equals 1. So that adds up to approximately 73% accuracy. So it's pretty good there. And so as results and actionable insights, I would choose to go with the decision tree model because it's easy to interpret, engaging for stakeholders. The strong predictors stand out at the top of the tree. And there's a handful of different ways we can use this model. Of course, most obvious is to classify future water source quality, but this model could also be pitched and sold to a variety of different organizations, like environmental groups or potentially factories or businesses responsible for pollutants, maybe construction or just environmental evaluation agencies that need to test ground or water levels before building anything near them. And this model can also be kind of a jumping off point for investigation into pollutant sources. So now that we know that chromium is kind of the most prevalent and the strongest predictor variable, and see where does that come from, why is it in the water, is it somehow natural, is it man-made, is it preventable, and we can also look at the correlated pollutants. Why did chromium have the highest number of correlated variables? So this could be not only the use case is not only future classification, but also a jumping off point for future research. And this about concludes my presentation. So thank you for listening.